Welcome to the lecture series on digital electronics 18EC 302C, and in today's lecture we are going to discuss about digital codes or binary codes. So specifically we are going to see the use of weighted and unweighted codes and list the various types of codes in these two categories, and also writing binary equivalent number for in specific codes like 8421 and XS3 code, and convert a given number into gray code and convert a given number from gray code to binary number. So at first we will look it into the classification of codes and the types of codes. So basically digital circuits use binary signals which are required to handle the data, which may be alphabetic, numeric or special character. That means you can see basically all the information that we want to process, the circuits has to process, may contain alphabets, both small and capital letters, and may contain numeric and may also contain special characters. But all these uh, rep- must be represented in binary format. That means whatever may be the type of data, that must be represented in the form of ones and zeros. So when we can represent every alphabet and every numeric and every special character, which is a part of the information or which forms the information that we want to process, then we can easily process that information by using digital circuits which can only understand ones and zeros. So to achieve this, a process called coding is required, where in that process each letter, special character and the numerical code numeral is converted into a combination of zeros and ones, and that combination is called as a code. And and we have a number of coding schemes, and in every coding scheme a different combination of ones and zeros represent a letter or a character or a numeral. So we will see the various types of coding schemes in this lecture, and also we'll find out how to convert the codes from one format to another format. So basically all the codes can be classified into two different types, uh, that is weighted codes, and the second one is called unweighted codes. So basically what is meant by weighted code means, so code means it's a set of or a combination of ones and zeros to represent any alphabet, numeric or special character. So it may contain number of positions, and in various positions you may find either a 1 or 0, because all these are binary codes. So if a particular code if in a particular code, if each position of a number represents a specific weight, that means the weight of the um, position weight for each position is different. So that particular code is called as weighted code, and in particular, since these are all the binary codes, it is called as weighted binary code. So we have various types of binary codes like BCD, the binary coded decimal, or it is also called as 8421 code, and also we have 84 minus 2 minus 1 code and 2421 code. So here the numbers represents the weights for the various positions of the binary codes, and this particular type of codes, weighted codes, are useful in circuits like digital calculators and voltmeters, etc. So where the code has each position of the code has a particular weight, and that is dictated by the particular coding scheme. So, and second category of codes belongs to the unweighted codes, and these particular codes have the property that they don't have any positional weight. That means they are obtained in a different way other than uh, giving a weight for each position. So now we have certain examples and important codes under this category. They are XS3 code and gray code. And basically, unweighted codes are useful in digital computers and shaft position encoders. So this is gives the broad classification of the codes and usefulness of the codes and various types of codes under the two categories. And next we'll discuss in detail some of the important types of codes under these two categories. Basically, according to the syllabus, we'll discuss the 8421 code under weighted category and XS3 code and gray code under unweighted category. So we'll first look at 8421, which is a weighted code, and we'll see how to represent a decimal digit. So this code is particularly used to represent decimal digits and numbers using binary digits, and we'll see how numbers and digits can be decimal digits can be represented using this particular code, and how to convert a particular BCD code into a binary equivalent number, and how to write a binary equivalent number for a given code in 8421 coding scheme. So here every decimal digit, so we have 10 decimal digits starting from 0 to 9 up to 9. So 0 1 2 3 up to 9. So we have 10 decimal digits. So each decimal digit is represented by its 4-bit binary equivalent. That 4-bit binary equivalent is called as BCD code. So 4-bit binary means by re remembering that the weights of the 4-bit binary are starting from the least significant bit, they are, you can see that they are 1, that means 2 power 0, and 2 2 power 1, this is 2 power 2, that is 4, and this is 2 power 3, so that is 8. So since the weights for all the 4 bits starting from LSB are 1248, or from MSB they are 8421, so this is called as 8421 code. So simply it is said that every decimal digit is, we have 10 digits, so every decimal digit is represented by its 4-bit binary equivalent. And since the 4 bits have the weights 8421 starting from MSB to LSB, so this binary coded decimal is also called as 8421 code. So here the table shows that decimal digit in the first column and the corresponding BCD code in the second column. Here you can see that for the decimal digit 0, the equivalent BCD code is 000000. So though it can be represented with a single 0, since BCD code means it should give 4-bit binary equivalent for a particular decimal digit, so we have to write 4 zeros, 0001, 0000, and for one decimal digit the BCD code is 0001, and similarly for 8 the BCD code is 1000, and for 9 the BCD code is 1001. So for 9, how we can write by the BCD code means here you can see that for the decimal digit 9, we need to add the weights for the positions where the bit 1 is present. So in 8 position 1 is there, and in 1 position 1 is there. So 8 plus 1 equal to 9. So this way we can write the BCD codes for all the 10 decimal digits. And if a number contains 2 digits, we have to replace the 2 digits with their corresponding BCD code. For example, you have the decimal number which is 99. 99, if you want to represent the decimal number 99 by using BCD code, you have to replace each 9 with its corresponding BCD code. That means first 9 is represented with 1001 and second 9 is also replaced with 1001. So the total BCD code for the decimal digit 99 will be 1001 1001. So this way we will represent any decimal number by its BCD code. So simply we have to replace simply BCD code is used to code the decimal numbers. So for the 10 digits we have given the binary code, and in the number whatever we want to convert the number into BCD, so replace each decimal digit with its corresponding BCD code. And normally this BCD code will be useful for input and output operations of digital system, because the humans will understand the decimal numbers very easily when compared to the digital systems. Digital systems will only understand binary. So binary coded decimals, that means coding the binary that is understood by your digital systems in decimal, will be helpful when you are doing input and output operations in digital systems. So then how we can convert, or how we can write binary equivalent for a given number in 8421 code, or given number in BCD code. So we'll understand this with an example. So here give the BCD equivalent for the decimal number 589. So we are given with the decimal number 589, and we have to get the BCD equivalent or BCD code for this decimal number. So this decimal number has 3 digits. So what we have to do? So to give BCD code for any decimal number, we have to see what are the various decimal digits that are present in that number. So here we have 5, 8, 9. 3 decimal digits are there. So from the table you can see that what is the BCD code for 5? It is 0101. So replace 5 with the BCD code 0101. Similarly for 8, find out what is the BCD code. It is 1000. So replace 8 with the BCD code 100. Similarly, replace decimal digit 9 with its BCD code 1001. So write all these 12 bits continuously or combinedly. So the code will be 589 BCD, or the decimal number 589 decimal number can be represented in binary coded decimal coding scheme as 0101 1000 1001. So here he will write, since 589 is a decimal number, subscript will be 10, and since this is a BCD code, not binary, so BCD code, so the subscript will be simply capital BCD. Similarly, we'll take one more example to understand how to write the binary equivalent for a decimal number. So here the decimal number is 69.27. 69.27. So here we found 4 decimal digits. So keep the decimal point as it is. So replace all these digits with their corresponding BCD code, 4-bit binary equivalent, that is BCD code. So 6 is replaced with 0110, 9 is replaced with 1001, 2 is replaced with 0010, 7 is replaced with 0111. So for the 69.27 decimal, 0110.00100111 BCD is the binary coded decimal equivalent code for this decimal number 69.27. So this way we can represent any decimal number in BCD coding scheme, and similarly we can convert any decimal number to BCD and vice versa. So next we will see, so this code will come under the category of weighted codes. So next we will see in detail about the two more codes. And the first one will be XS3 code. And here what is in the XS3 code we'll discuss, and we'll also see how to convert a given decimal number into XS3 code. So XS3 code is also used to represent the decimal numbers, but before going to see how decimal number can be converted or represented in XS3 code, we will see how to represent the first 10 decimal digits in XS3. So if we can represent 10 decimal digits in XS3, then we can represent any decimal number in XS3 simply by replacing the decimal digits with their XS3 code, similar to the BCD. So here what is in the XS3 means, here before converting, so here also we'll write the 4-bit binary equivalent of the decimal digit, but not for the actual decimal digit, but it is for the decimal digit plus 3. So that means when you want to write the decimal XS3 code for 0, we'll add 3 to this decimal digit, so then it becomes 3, and for 3 we'll write 4-bit binary equivalent, which is 0011, which is 0011. Similarly for 1 we'll add plus 3, so it becomes 4, and 4 I will write the 4-bit binary equivalent, it is 0100. Similarly for 9 I will add 3, so then it becomes 12, and for 12 I will write 4-bit binary equivalent, it is 1100. So in this way we can get the XS3 codes, or we'll get XS3 codes for all the 10 decimal digits. So simply we'll add 3 to the decimal digit that for which we want to write XS3 code. We'll add 3 for the decimal digit, and for the result we'll write the 4-bit binary equivalent, and that becomes the XS3 code for the corresponding decimal digit. And here using by looking at few examples, we'll see how to convert a given decimal number into its XS3 code. So the first example is convert the decimal number 367 into its XS3 code. So what we have to do? So since we have to see what are the various digits in a particular number, and in this particular number the decimal digits are 3, 6 and 7. So for each decimal digit you have to replace the digit with its XS3 code. So to write the XS3 code for a particular decimal digit, what we have to do? We have to add 3 to it, and for the resulting decimal digit decimal number, we have to write 4-bit binary equivalent. So here the decimal numbers are 3, 6 and 7. I add 3 to each digit. So 3 plus 3 is 6, and 6 plus 3 is 9, and 7 plus 3 is 10. So here its 4-bit binary equivalent, 9 with its 4-bit binary equivalent, 10 with its 4-bit binary equivalent, and this combined number becomes the XS3 code for the decimal number 367. So this way we can easily get the right XS3 code for the given decimal number. Similarly, we'll see one more example where we have to convert the 58.43 into its XS3 code. And what we are doing the same thing, that we will identify what are the decimal digits this number. They are 5, 8 and 4, 3, and for each decimal digit you add 3. So 5 plus 3 8, 8 plus 3 11, 4 plus 3 7, 3 plus 3 6, and for this 8 you replace with its 4-bit binary equivalent, and for 11 and for 7 and 6 also. You combine all these bits and this becomes the XS3 code for XS3 code for 367. Sorry, this becomes the XS3 code for the decimal number 58.43. And this way, this is how we can represent, we can write XS3 code for any decimal number, and we can easily convert the given binary and given decimal number into its XS3 code. And next we will see one more coding scheme. It is called gray code. So gray code will come under the unweighted codes. So that means it doesn't have any positional weights. So it is obtained in some different way, not by using positions and their weights. So mainly very important code, gray code is useful for shaft encoders and some types of A to D converters. So we'll see how a gray code can be obtained. So normally gray code can be obtained from a binary number. So most of the times we may be getting the gray code from binary number, and sometimes we may be required to convert back the gray code to binary number. So first we will look at how to convert a given binary number into gray code. How we can obtain a gray code from a given binary number. So what are the various steps to obtain a gray code from a given binary number is, so binary number means you have that MSB and LSB. So that means the leftmost bit is called most significant bit and it is called MSB, and the rightmost bit of a binary number is called LSB, so it is called least significant bit. So we'll start converting a given binary number into gray code starting from MSB. So for a for the gray code, we'll start writing the gray code will be start writing from the MSB bit to the LSB bit. So what can be the MSB bit of the gray code for a given binary number? So the most significant bit of the gray code is same as the most significant bit of the binary number. So whenever you want to convert a binary number to gray code number, so for the gray code, the MSB is same as the MSB of the binary number. And then what about the other bits? The second bit that is to the right of the MSB, that is next to the MSB of the gray code, equals the XOR of the MSB and second bit of binary number. So the next bit of gray code equals the XOR of MSB of second MSB and second bit of the binary number. And when you take the XOR, if both the bits are same, then the result is 0, and if both the bits are different, the XOR operation gives you 1. And next, and how to obtain third bit? So third bit of gray code equals the XOR of the second and third bits of binary. That means X to obtain the bit for gray code in any position, we have to take the XOR of the corresponding bit in the binary and its previous bit. Right, so this is very simple, but it will be very clear if we can illustrate with an example. So here we go with an example to convert the decimal number 564 into gray code. So here we are given with an example where we need to convert the decimal number into gray code. We cannot convert the decimal number into gray code, so first convert the decimal number into its equivalent binary. So this we can do by the continuous repeated division by 2. So by repeated division and collecting the remainders, the 564 can be converted into binary number, which is 100 and 110100. So this is the binary number, and this number we need to convert into gray code. So how to convert gray code? By following the above steps that we can see clearly here. So what we have written at the top is the binary number or binary equivalent for the 564, and at the bottom we'll start writing or start obtaining the gray code starting from the MSB, and you can see that for the gray code MSB is same as MSB of binary. So MSB of gray code is 1, which is same as the MSB of binary. And what will be the next? How to obtain the next bit of the gray code? So the next bit of gray code can be obtained by XOR, by performing XOR operation between the corresponding bit and the previous bit of binary code, that is 0 XOR 1. Since both the bits are different, the result of XOR is 1, and this will be the next bit of your gray code. And similarly, how to obtain this bit of gray code? Perform the XOR operation between corresponding bit and the previous bit of the binary, that is 0 XOR 0. Since both the bits are same, the result is 0. So in this way we can obtain all the bits up to the LSB. So for the LSB bit of gray code can be obtained by XORing the LSB bit of binary and the previous bit of binary. Here both are zeros, so both are similar. So XOR results in 0, which will be the LSB of gray code. So this is how we can convert a given binary number into gray code, or a given decimal number into gray code. So whatever number you want to convert into gray code, first convert that into binary number, and binary number can be converted into gray code by following these steps. That means the LSB of the gray code will be same as the MSB of the binary, and for any other position the bit in gray code can be obtained by performing XOR operation for the corresponding bit in the binary and its previous bit. And if both the bits are same, XOR operation gives 0, and if both the bits are different, XOR operation gives 1. And this is how we can convert a given binary number into gray code, and a very important code. So we have to practice how to convert a given binary number into gray code. So next we'll see the opposite conversion also, that is how to convert a given gray code into binary. So here this procedure list shows what are the steps that can be followed, that should be followed to convert a gray code into equivalent binary. So here also you can see that, so here also we'll start converting the binary bits into Gray code starting from the MSB. And so we are converting from a given Gray code to binary. So we'll start with MSB, and the MSB of binary number is same as MSB of the Gray code. MSB of the binary number is same as the MSB of Gray code, and so this is those two MSBs are same. So the MSB of the Gray code we have obtained. Then how to obtain the remaining bits of the Gray code? So the second bit, the next to the MSB of, that is the second bit of binary can be obtained, or binary equals the XOR of the MSB of the binary and second bit of the Gray code. So to get the second bit of binary, what do you have to do? You have to perform XOR between the corresponding bit of the Gray code and the previous bit of binary. Previous bit of binary. So if both are similar, then XOR gives 1, XOR gives 0. If both are different, XOR gives 1. And this is how we can obtain all the bits of your binary number from the corresponding bits of Gray code. So for example, the LSB of binary number can be obtained by XORing, by performing XOR operation between LSB of Gray code and the previous bit of binary number. So we'll see an example here. We have taken example how to convert a Gray code 101101 to binary. So here we are given with a Gray code. 101101 is a Gray code, and this must be converted to binary. So here we look at in detail how to obtain a binary number for a given Gray code. You can see that at the top we have written all the binary bits and Gray code bits 101101, and at the bottom we'll start obtaining the bits for the binary number. So we'll start with the MSB, and the MSB of binary is same as the MSB of Gray code, and to obtain the next bit of binary we'll XOR the corresponding bit of Gray and previous bit of binary. So 1 XOR with 0 gives 1, because 1 both are different bits. And similarly, to get the next bit of binary, we will XOR the corresponding bit of Gray and the previous bit of binary, that is 1 XOR 1. Since both are similar bits, XOR gives 0. So in this way, to obtain the LSB of the binary, we will XOR the LSB of the Gray code and the previous bit of the binary, which is 1. So 1 1 similar bits, the result is 0. So 110110 will be the binary equivalent binary number for the Gray code 101101. So this is how we can obtain the Gray code from a given binary number. So far we have seen how to write a BCD code, and how to write XS3 code, and how to write a Gray code for a given binary number. and vice versa. So all these codes have very practical importance. So better understanding of all these codes are required for understanding of digital circuits. So by reviewing what we have seen so far, so we have looked at the various classification of the codes into weighted and unweighted codes. So where weighted codes have in weighted codes, each position of the number represents a specific weight, and that type of coding scheme is called weighted binary code. And the various types are we have number of weighted codes coding schemes, and out of which we have studied binary coded decimal, simply called BCD code, or also called as 8421 code, as this code has the positional weights 8421 starting from LSB to MSB to LSB. And in particular, these weighted codes will be very useful in digital circuits like digital calculators and digital voltmeters, where we will the devices have some displays in the decimal form. And we have another classification of the codes. It is called as unweighted codes. And here these codes are not positionally weighted. So basically, they are obtained with a different method. And among unweighted codes, we have seen in detail XS3 code and gray code. And basically, these codes are useful in digital computers and shift position encoders. And here in this slide, we have seen how we can obtain a BCD code for a given decimal number. So first of all, we have obtained the BCD code for the 10 decimal digits, and after that we have seen how to obtain the BCD code for any decimal number. To obtain the BCD code for any decimal number, we have replaced each decimal digit with its corresponding BCD code. And next we have seen what is XS3 code and how to obtain the XS3 code. So here also we use this XS3 code to convert any decimal number into the XS3 code scheme. And here how to obtain XS3 code for 10 decimal digits. Uh, for that decimal digit we have to add 3, and for the resulting decimal digit or number you have to obtain 4-bit binary equivalent, and that 4-bit binary equivalent becomes XS3 code for the corresponding decimal digit. So after that we have seen how to convert a given decimal number into XS3 code. So here also what we have to do, already we have obtained the XS3 codes for the decimal digits. So here convert, replace each decimal digit with its corresponding XS3 code. So with that we will get the XS3 code for the entire decimal number. Next we have seen what is gray code and how to obtain a gray code for a given binary number. So how to obtain a gray code for a given binary number means so we will start obtaining the gray code for a given binary number starting from the MSB bit. And the MSB bit of the gray code is same as the MSB bit of binary. And the next bit of the gray code or any other bit of gray code can be obtained by performing XOR operation between the corresponding bit of binary and its previous bit. And if both the bits are same, the XOR operation gives 0. If both the bits are different, the XOR operation gives 1. And similarly, we have seen the other conversion, the reverse conversion operation also, that is to convert a Greek code into binary. And here we have also seen the procedure of how to convert a given Greek code into binary. So here also the conversion procedure starts with MSB bit position and ends at LSB bit position. And the MSB bit of the binary is same as the MSB of the Greek code. And for any other to obtain any other bit of binary, we have to perform the XOR operation between the corresponding bit of Gray code and the previous bit of the binary. So, but this procedure of conversion should start at MSB and should proceed towards LSB. So, overall we have discussed the various codes, the classification of codes and the types of codes, and how to convert a given binary number into the various coding schemes like 8421, SS3 and Gray code and vice versa. So the coding codes will play a very important role in the digital circuits where we maybe need to convert or the circuits may be need to convert from one coding scheme to the other to facilitate the human to understand the digital systems. And in the next lecture, we'll be looking at we'll be looking at the Boolean algebra and some of the basic gates that will be used in digital electronics. And this completes the lecture on code sign, digital code sign conversion within the